you can start it. Yeah.
Okay. Okay.
Yep. Mm. Okay. Yep.
Have you seen my PPT, right?
Yeah. Yes. Yeah.
Okay. Okay. Good morning to everyone. Today I would like to make my presentation based on the deformation effect of deep foundation, field excavation, and retaining structure and a digestion software station. So when you look at the topic of the article, those are the authors, those who wrote the article, and the article was published in Scopus. If the journal is uh, Journal of Building, and they publish it in Scopus. So the one who will present today, I'm by name Abraham Yuen Ngong Deng, and I will take you throughout of this deformation effect of deep foundation, feed excavation, on retaining structure and the just subway station. The deep foundation is affected by encompass complex interaction of structural, geotechnical, and environmental factors. Understanding and controlling this effect through proper support design, construct sequencing, monitoring is crucial for ensuring safety or safe urban construction, particularly near sensitive infrastructure such as subway system. Uh, Regarding to this, we will be talking about the background of the article. We look at the background, the challenges of urban development, numerical stimulation for prediction, and then the location of the research article where they take their research, and also the foundation feed support system, excavation three-dimension and numerical simulation. We look at also the three-dimension numerical calculation models and feed excavation step with their process. Also, we look at the excavation process and deformation, as well as feed and software structure effect analysis. We look at also the excavation support structure deformation analysis and tunnel station structure deformation analysis, surface settlement analysis, numerical simulation and field monitoring comparison, and the conclusion plus the future direction. This is the whole overview of the article, and that is what I will present. The research background, we look at three things. Urban development pressure. We've seen when I read the article, there are three things that I have seen, that I have read. Urban development pressure, uh, primary engineering concern, and technical concern. On the part of urban development pressure, the writers or the authors say increase in construction of highest building necessity, deep foundation feed excavation. Also, urban planning face several challenges like cities becoming more dense developed. And they say also these days, deep excavation projects are becoming more prevalent in complex underground environment. On the part of primary engineering concern, they also say deep foundation feed excavation cause a well-spread soil uploading and disturbance. And they also say this soil movement diversely affect the stability of nearby subway facilities like tunnel and station. So there is a need to balance the construction requirement with the protection of existing underground infrastructures. On the technical concern, they also say there is need of reasonable foundation field support schemes, which are essential to minimize the soil disturbance. And also there is also a need of proper support structure and construction techniques can also effectively control soil deformation and settlement. Protection of subway structure stability is also crucial for urban transportation safety. Those are the background of this article. And the reside gap, what would they say the reside gap? Many studies, they explore the foundation feed stability using numerical simulation, but there is that lack of comparison with the field monitoring data. There is also another, they say there is a need of validating methodologies to predict and control deformation effect on complex existing underground structures. And also the most important thing that the most important thing that they suggest is the demand of safety, efficient, and economic construction method for deep and large foundation near software facilities. So those are the research gaps that I read and found in the article. So the challenges of urban development, they also say rapid urbanization increase the demand of high-rise building, lead to more deep excavation project. And number two, they also say soil uploading, there is always deep excavation cause well spread of soil uploading, which impact the stability of nearby subways. And also number three, they say on the issues of support scheme, there is a reasonable foundation feed support, which is crucial to minimizing the soil stability and protecting the subway structures. So on the numerical stimulation for prediction, the authors use numerical to dispense for predicting the effect of soil excavation on structures. This study, they use the accuracy, they want to confirm the accuracy of LAX 3D software in reflecting soil pressure and deformation during the excavation. The authors also use a numerical calculation to study structural performance and also explore the innovative support system like T-shape file and also H-shape steel to balance the stability and the green economic. So the site of research, this is the location of the research and what they design, the location of the research in Nasun district of Shansai with the total area site of 36,268 meters square. The subway, they also have subway line 2 fast on the northern, if you look at the metro line, and also the subway that they design. So on the foundation depth is also 15 to 24 meters, which is a special safety assessment is required to proximity to metro security area. So this is their research location that they carry out the research and make the article from. Foundation field support system. There are four things that they are applied. The interlocks file. They say the interlock file are used for support on more site, made of 3 reinforced concrete, C30 reinforced concrete, and a digestion wall. They have the existence of 0.8 meters thick of wall on the location from Hong Shouwan source station is used as a temporal support. Also, there is internal support. There are 3 reinforced concrete structures used for internal support with supporting beams. And also they have waterproofing, the interlocking file and existing digestion wall are supplemented by the high pressure jet ground. So the three dimension calculation, this is what they design based on what you have seen before the location. They say the purpose of this software is to analyze the soil stress release and support the system deformation and environmental impact from the excavation process. So A and B plus C, it is analysis. They use Plug 3D software for numerical simulation to model the foundation feed excavation in 3D. The dimension, this is the table of the make calculation regarding to the stimulation, and they use more column model formulas. So this is the length, the foundation feet, and the model dimension plus the dimension composition. They use this table also for physical and mechanical property of the soil, like natural wedge, coefficient, internal angle friction, and also the modulus. So, and the soil facial ratio. So this is the table they use when they design. And also the feed excavation step and the process from internal stress balance, excavation 1, support 1, excavation 2, support 2, excavation 3, and support 3 plus excavation 4, with their all implementation process plus elevation and excavation thickness. So the picture show the excavation process and deformation. Regarding to what the researcher designed, there is first reinforced concrete internal support, and also the second reinforced concrete support internal support, and the third reinforced concrete internal support. On the other side, they use bit file, and at the bottom the bottom of foundation feet. So there's the excavation process in divided into 4 steps with support with the support constructed after each step. The maximum lateral displacement concentrate in the middle of the support structure form an inward convex curve. This adjacent or contiguous wall segment show the smallest displacement, 19.42 millimeters, compared to the bit file strength with 38 bit file strength segment with 38.89 millimeters. So the bit file they put on the inward convex curve, that is the use, and the feed and structural impact analysis. So they make the estimation and they find out that the structural design, the project used bit file and a digestion wall with reinforced concrete internal support to prevent the deformation nearby subway, tunnel, and station in soil soft condition. Displacement patterns. A maximum lateral displacement occur in the middle section of the support structure with the minimum movement at the top and the bottom due to the great bottom constraint and reduce the lateral pressure at the top. The excavation effect. The maximum horizontal displacement increase progressively with excavation deep, while top and the bottom section maintain a relatively small displacement throughout the process. So A and B, A is the displacement of engineer engaging file, and B is the displacement of underground diaphragm wall that during the excavation to the bottom of the foundation feet. On the excavation support structure internal force analysis, we have three: A, B, and C. A is the bending moment. The bending moment is larger in the middle and smaller at the top, and also smaller at the bottom. The digestion wall has a smaller variation than the bead file. Also, the A is a bending moment and B is axial forces, relatively balanced with the largest force near the junction of the bead file and the digestion wall due to the stiffness difference. So you can see the models or the picture which they analyze and the result of axial force. The maximum values of a digestion or contiguous wall is 2.38 times 10 raised to power 6 Newton n meters, and support file is 4 times 9 4.9 times 10 raised to power 6, and the internal support is 8.42 times 10 raised to power 6. So indicate that the bending moment is large at the middles, which is picture A in the middle part, and also smaller at the top and at the bottom as well. The other one is tunnel and station structure deformation analysis. They use this table to analyze the displacement from that X and Y. The total maximum station displacement is 8.7, and also the metro line is 2.29. This analysis indicates that overall deformation of the station and tunnel lining is maximal or small, primarily due to the distance and the digestion wall, suggesting the low construction risk. So this is the analysis of underground or tunnels, and the indication of this showing that the distance or the deformation is low. Why? Because due to the distance and the digestion wall, there is a low risk of construction here. So that indicates there is no, the designing of underground tunnels is okay. So the surface settlement analysis, the design, they have 4 points. The monitoring setup observe point A to point B, point A to point B are replaced on the southward near the subway entrance and on the east-west side to monitor soil disturbance and from excavation. Also, point A and point A to point D and point A to point B are bit file support showing overall settlement trend with a similar maximum settlement values during the excavation. Point C and D are on Hong Chongwan South Station entrance, showing no significant settlement or uplift due to 0.8 meter thick underground digestion wall protection. And the last part is their recommendation regarding to the design of settlement analysis. They say appropriate support structure should be selected based on the actual site condition to achieve optimal soil control and environmental protection. Numerical stimulation and monitoring comparison. So the monitoring-based stimulation, the study showed that the actual horizontal displacement of support file is smaller than the numerical simulation prediction, with the monitor values showing the consistent with a stimulation trend overall. The construction environmental impact, the post phase here, they show the comparison. The post phase excavation show a low interclimater values than the third phase that show the, the depths likely due to disturbance from the surrounding construction project at the complex side by side, and the safety of performance of this design. The maximum displacement range from 28 to 86 millimeters point at the source site, protected by existing 0.8 meters adjacent wall to 32.57 meters on the other direction, all of which are below safety standard, confirming a good fit stability and a low risk construction. And to the conclusion and the future direction, the support structural performance, the study revealed that a small lateral horizontal displacement is resulting in inward and internal convex curve that digestion will perform better than the bit file. The internal forces, when we see the stimulation before, bending movement are large in the middle, and internal support forces are uniformly distributed. Subway safety, a minimum displacement of subway station and tunnel confirm a low-risk construction, and also on the part of surface settlement. The analysis show that the overall settlement trend with a digestion wall support show the less settlement. And the future direction, there is a need to optimize the internal bracing beam across sectional site for economic and safe construction. Up to this juncture, I would like to say thank you for your attention, and I would like to stop here for my presentation. Thank you.
Okay, thank you, Brian. I think what we can learn from this project is actually the internal bracing which they use is quite different with what we teach in the class, right? Because in the class, what we talking about, if I believe this is a bottom up case, right? Not instead of top down. So does anyone remember what we talk about? Say, what's the supporting system we can use for the bottom up system? Anyone remember?
I think the one that we used last time, I remember there is in Climata. Also, they talk about in Climata also for monitoring.
That's about the interpretations. But if we're talking about a starting system, the supporting thing we use H type steel or use anchor, right? Yeah, but this case they use a reinforcement concrete. That's something quite interesting because in Taiwan we hardly saw any reinforcement concrete starting in Taiwan. But in mainland China or even in Singapore, I think some cases they do use that. That's so I mean and so far I don't know which one is better. I mean that's kind of issues which probably later on we can explore a little bit more. But again, by looking at the model which you have, actually the subway station and the tunnel are at the two sides of the excavation, right? Yeah, because the station is just like the figure you have is at the let's say the downside of the excavation, and the tunnel is in the other side. But I feel a little bit confused. He say, well, I think one of the conclusion it says because the station is far away from the excavation.
mm.
Oh, but so that's the reason why the station is safe, right?
Yeah,
Has a minimum. But in fact, I think the station actually is next to the site
yeah.
by the layout. So why he say is why the paper says far away?
Okay, yeah, that is a good question. They also
Yeah.
said, yeah, that is they said actually for
Mm,
due to the security of
mm,
the due to the security of the tunnel or the security of the subway,
mm,
there must be a distance so that it prevent the risk. Maybe if there is kind of the accident, then it
mm.
will not affect the side where the people are living in. That is what they say in their papers.
Yeah,
And
yeah,
mm,
in the model, in fact, it's not.
yeah, this one, right?
Yeah,
Yeah,
it's not. Yeah, because why I have an interest because one of student in my team we are talking about say if you have an excavation
mhm,
existent excavation nearby, what will be the impact on the ongoing excavation? For example, will it increase the deformation of the excavation? I mean the wall deformations. I mean, you think about how
yeah,
you not not
okay,
not
Professor.
not, not
But Professor,
yeah.
what they say regarding to that, they say because the reason why they use because they are having two. One is concrete, reinforced concrete file, and
Yeah.
also they use bead file. They say the reason why they use the bead file in the middle to
Mm,
form the curve is because to prevent
mm, mm,
the deformation of nearby subway tunnel
mm,
and
mm,
station in the subsoil. That means why do they use for a long is because to prevent I think the deformation. Maybe if there is deformation in the
mm,
tunnel in the subway
mm,
and subway tunnel, that means it may form the deformation in a subsoil. So that's
mm,
why they use a bit file so that
mm.
the subway should be far from the stimulate
Yeah,
the building discussion.
I agree that very likely
Mm,
say
mm,
no matter the station and the tunnel is not that close to the excavation. Otherwise, it shouldn't be
mm,
the case. I mean,
mm,
okay, if that's the case, okay, when I teach you how to calculate the stabilities, right?
mm,
Stability of the excavation,
mm,
how we gonna to calculate? Because I mean, for us to do the excavation calculation, one side is retain side, the other is excavation side. But in fact, in the retain side, if they
mm,
two excavation next to each other, and then
mm,
it will not be the soil,
mm.
it will be a structure itself.
Yeah, yeah.
Yeah. Yeah. Oh, so anyway, I think that's some details which we will have to I think we could dig more into that, but I don't think we will have time today. Because it's already nice early.
Mm.
Supposedly, I think you guys only allow 7 minutes, to do a presentation, and then including the discussion, we already spent like 20 minutes for that. So yeah. Anyway, so thank you for your presentation today. I mean, I think it's quite interesting. That's from a journal paper or conference paper.
Yeah, journal paper.
Journal
Journal
paper.
paper.
Okay. Yeah.
Yeah,
So
they publish it in I think in
mm,
Q2 in Scopus.
okay. Okay. Yeah. Anyway, that's quite interesting and many details we should be able to dig into that. Okay. Oh,
Mhm.
so thank you. So next will be
Thank
that.
you.
Yeah. So next will be Desmature. Desmature, are you ready?
Ready, Prof.
Okay. Yeah. Please.
You see my PPT?
Yeah.
Okay. Good morning, everyone. Today I want to present a three-dimensional analysis of deep excavation on Taipei 101 construction project, understanding wall corner restraint effects by Dr. Lin DG and Wu, 2007. Okay, why this study important? When we dig deep holes for building basement, the walls can move inward. This movement can damage nearby building and underground utilities. And next, this is the location for the project at the Taipei, Taiwan, for the 101 floors and 508 floor tall. And the basement is 5 floor underground. So the excavation depth is 21.7 meters. And the construction start in 199 to 2002. So the excavation zone have the two zones. The first one is tower zone. For the tower zone is with bottom up method and steel strut support, and podium zone is top down method with concrete floor slabs. And next, this is two different construction methods. With the bottom up at the tower zone is dig down 4.4 meter with the installed steel strut and dig deeper. This method is repeat 6 times. And next is power concrete made at the bottom. And for the top down is wood walls first and dig down a little with concrete floor, dig under the floor with neck floor below, continue the bottom. And as you can see the picture, the different podium zone and the tower zone. Understanding the plane strain ratio. The plane strain ratio is maximum wall movement from 3D analysis time per maximum wall movement from 2D analysis. And as we can see, the one is PSR1 has no corner effect, and for the PSR1 0.7 is moderate corner effect, and for PSR 0.4 is strong corner effect. This 3D movement, as you can see, for PSR 0.7 is 70% of 2 dimension, and for the PSR 0.4 is 40% of 2 dimensional. How was this study conducted? The first one is field monitoring, is inclinometer measure wall movement, and the second one is settlement point measure ground sinking, and they use piezometer measure water pressure. And for the computer modeling for three dimension and 2 dimension, use actual soil properties from 128 boreholes. And next one, simulate is construction step by step and included groundwater flow analysis. And the last part is comparison. Compare 3 dimension and 2 dimension prediction. compare prediction and actual measurement, and calculate PSR values for each excavation stage. For the results, as you can see, PSR decreased from 0.73 to 0.44. As excavation got deeper, this means corner effect becomes stronger, not weaker, despite adding more steel supports. And for the top-down method, the SR increased from 0.32 and to 0.61, but still remain well below from 1. Corner effect were present throughout, but concrete floor slab gradually reduces the corner influence. Why the wall corner reduce movement? Without corner, wall can bend freely. Only horizontal support resists. Maximum movement occurs like a simple beam. For with corner, with 3D analysis, corner acts like a vertical support. Adjacent wall help each other. Movement is reduced like a beam with additional support. The factor influence the corner effect is distance from corner. Effect are strongest near corner. Wall strength ratio. Shorter wall shows stronger corner effect. Soil condition. Soft soil below excavation increases corner effect. What does this mean for engineers? For design implication, engineer must use 3D analysis for excavation with low L/A ratio. Using only 2D analysis will overestimate wall movement and lead to overly conservative and expensive design. When we use the 3D analysis, when excavation section within 1.5 horizontal from corner, LH ratio less than 3.5, when accurate prediction are critical for nearby structure. For design implication, can rely on support system alone to eliminate corner effect. Corner effect persists even with a very stiff support system. Different support types show different behaviors. So the conclusion, corner effect are real and significant. While corner reduce lateral wall movement substantially even with heavy support system, PSR value range from 0.32 to 0.73, indicating 27 to 68% reduction in movement compared to two-dimensional prediction. And the second one, support system cannot eliminate corner effect. Neither preloaded steel struts nor corner concrete floor slab could suppress the restraint effect of the wall corners. For the 3D analysis is essential. For deep excavation like Taipei 101, 3-dimensional compositional model are crucial, predicts realistic deformation behavior. And for the 2-dimensional analysis, consistently overestimate wall movement. And that's all from my presentation. Thank you so much. 谢谢
Okay, thank
大家。
you. Yeah, thank you. Yeah. I think I think probably two key issues I need to address here. Okay, first of all, why the PSR? I think I did teach that in the class. Okay, why PSR? We need to divide by 2D, the 2D analysis result. Why?
Because 2D analysis can the corner effect measurement. So they need a 3D analysis to see what happened in corner effect.
Yeah, we need a 3D, but do you remember the definition of the PSR? Why we are 3D divided by 2D? Why is 2D?
Why is 2D?
Why is 2D? Yeah, because sometimes I worry, say maybe in the class I didn't explain very clearly by having the presentation you have today. I mean, easier for me to explain that again. Okay, why 2D is 2D for any 2D analysis which we have for geotechnical engineering analysis. That's the plane strain case. Plane strain case means okay, your your case is extended very far away in longitudinal directions.
Mhm.
So we call it the plane strain condition. So plane strain condition means not affected by any corner effect at all. So that's the reason why they take 3D divided by 2D. Because 2D means the plane strain condition, PLANE, plane strain condition, which means your case is extended in longitudinal directions, say very far away. So no corners effect
No,
is going
no
to
corner.
no corner effect is going to affect of that. So that's the reason why we need to use, you need to use a 3D divided by 2D. The main reason is 2D result give you a plane strain condition results. So that's the reason why you need to divide by 2D. Okay.
Okay.
Okay, that's the first things. And the second thing that I want to I want to mention about the so the 3D analysis conclusion is from the paper say, you must for very crucial one that's come from the paper, or because in your conclusion you say 3D is important, we need to use 3D analysis, or that's from the paper itself, or 3D analysis is
It's
essential.
crucial.
That's from the paper itself, or from
The paper.
the paper. Okay, but I want to remind you one thing. Yes, 3D is okay for any more complicated cases. Yeah, we need to run 3D, but you need to run 3D correctly. For example, if any conditions there, okay, are not consistent with what really happened in the ground. Let's say the any mechanism during the excavation is wrong, and you run 3D, and I would say that's garbage in, garbage out, because the mechanism is not, or not consistent. And the second thing is very important for 3D is you have to put in you need to put in a reliable input. For example, if you run the 3D, but your soil parameters are totally, say, unreliable,
Oh.
whether or not you are going to get a correct answer, right? So right now I think, okay, of course in Taiwan most of the engineering people they prefer to run the 2D, but I would say 3D definitely has a need. So that's a reason why some company they come to us to run a 3D analysis. But again, what I want to address is, okay, you ask us to run a 3D, but to the end, what you can provide to us, the only soil parameter is SPDM value. And then what? You don't have any reliable input, and you only ask us, you only give us SPDM value, ask us to assume many things. It doesn't make any sense, right?
Yeah.
So that's the reason I say, okay, in addition to 3D analysis, I think other two things, in the 3D analysis itself, the mechanism which you have must be correct. But in addition to that, the reliable SI soil investigation data. So that's the reason why, I mean, at the very beginning of the class, we talk about SI. And also the final week of the class, we talk about what, remember? In the classroom, what we talk about is
Inclinometer.
no. I think we talk about monitoring system, right?
Yeah.
So these three parts actually are all very important. SI reliable, SI give you a reliable parameters, and the monitoring actually a reliable monitoring system can provide you a reliable monitoring result to feedback whether or not your input is correct or not, your output is correct or not. So these three elements, I think, is quite important for the excavations. Yeah, but I think many people not pay attention to this. So these are two things which I would like to comment, in the papers today. Okay. Yeah. Okay. Yeah. Thank you. So next one, Moriarty, morning. Yeah.
Good morning.
Yeah.
Okay, let me share.
Yep.
Oh, is it share? Are you seeing anything? Share content.
Oh, not yet.
No, not yet.
Not yet.
One moment.
Before Moriarty is ready, I mean, can you all say turn on the camera, because I think Coco wants the one screenshot to have everybody on the computer. So can you turn on, because now Moriarty not yet ready, so can
Sorry,
you
I
all,
don't have camera.
you don't have a camera? Okay, so
Yes.
Mickey, I don't think you are that poor, so you don't have a camera.
I'm using the computer.
Okay, that's
Not
fine.
laptop, so I don't.
Okay, that's fine. Yeah,
Sorry.
but for the rest, please, yeah, and I can send it to Coco. Yeah, and Majid, Tawfiq, and Moria, I think he's still working on his. He's still working on it.
Oh, can I share
Oh,
now?
okay. Yeah. You can end it now. Yeah. So Majid doesn't have a the.
I try to open it, but it shows some privacy process.
Okay.
I try to open it.
Wait a second. Yeah, but I mean, Marais, can you temporarily not share the PPT, because I'm going to take one screenshot, because
Oh, okay.
yeah, let me take a, because I'm waiting for, yeah, okay, I can send it to Coco. Yep. Let me try it. Screenshot. rectangular. Okay. Yep, I think it should be okay now. Yep. Thank you. Yeah, so Moriarty, you can do it. You can go ahead to do the presentation.
Okay, so my presentation today is about deep excavation. Can you see my? Can you all see?
No, there is no screen share.
Yeah,
Missing,
it's
missing.
disappeared.
Disappear.
Disappear.
When you enable it, it disappear. Maybe you enable it first and then you screen share it.
Okay. Let me share.
Moriarty, are you in the office or in where?
No, I'm in the office.
Yeah, but how come our office's internet is that poor? How it could be?
Sorry, you're saying
I
our
said,
office
how-
is?
Yeah,
Okay, now it
now
is
it's
now
clear.
it is visible. Now it
Wi-Fi.
is visible. Okay.
Yeah.
Okay, so
Hmm.
this is a paper about impacts of on the maximum lateral displacement and adjacent shield tunnel from ground stiffness of an excavation. This paper is by an author called Meng et al. And Professor Benson is a co-author in this paper. It's a very interesting paper to read and very nice, very detailed. I think it's slightly similar to what Abraham presented, because it also deals with an adjacent tunnel and deep excavation. So from what you can see, this paper was published in a journal called Tunneling and Underground Space Technology. It will appear in print, I think, in January 2026. It deals with deep excavation, plane strain ratio, ground stiffness, maximum wall deflection, and shield tunnel deformation. So it really explores how does an adjacent tunnel affect a deep excavation, and also at the same time, it will explore how the tunnel is affected by the deep excavation. An existing tunnel is affected by the deep excavation that is happening. So as you can see beside on the image I'm showing there, the deep excavation is the one in bold black below, and then you can see the existing two tunnels. Two tunnels are existing. On the top side, you can see that this project is situated, is a case study from Wuhan city in mainland China. And one of the things you notice is that they did not use a diaphragm wall, rather they used retaining piles. And you can see here at the bottom, on this side, bottom left, the piles, the retaining pile, and then there's an interjecting jet grouting pile, which was used because of permeability. They wanted to reduce the permeability. But essentially, the retaining system consists of 1.2 meter diameter retaining piles. This was the case because the ground had very good stiffness, so they did not need a diaphragm wall. This is the image of the site. So if you look at this corner here, you can see the entry to the train station, the subway station. And then you can see the deep excavation that was being done here. So those are the existing twin tunnels could be somewhere here. So we are going to explore the relationship between excavation-induced ground movements and tunnel deformation. That brings me to the cross-sectional view of the works. I said this is an excavation line, an excavation in parallel to line number 5 of the rail transit line in Wuhan, China. The main soil layers include the miscellaneous fill up to around 2.5 meters. There's residual soil up to around 4.3 meters, and then you have strongly weathered mudstone up to around 16 meters. And what do you have? Medium silty weathered silty mudstone for the rest of the profile. But essentially, you can see an excavation there that is about 21 meters. And then you can see the two tunnels on the right line and left line, and they are varying distances from the excavation. That can be seen by this figure, where at some point it's actually 4.6 meters away, and at some point 5 meters, and at the farthest end here you can see the excavation is about 9.4 meters away from the excavation. Excavation is from the station, basically varying distance between the twin tunnels and the excavation now being done. So to be able to then get the data for this, there required some instrumentation. There was some instrumentation that was done on the tunnel, on the existing tunnel, especially the right line or the right side of the tunnel. And the instruments that were installed include vibrating wire strain gauges. The prisms, if you remember, the prisms are used as surveying monuments. Then inclinometers that were installed in the pile retaining wall to check deformation. And on this segment, tunnel segment, there are two kinds of strain gauges that were here. There's one that is measuring longitudinally, meaning as along with the tunnel, the direction of the tunnel. And also there is a vibrating wire strain gauge that is measuring strains in the circumferential direction. So then what did we get? Some ground responses from across the various stages as the excavation continued. Now this is the deformation one. On the first figure, or on the same figure but on the left hand side, is the ground settlement, and on the right hand side is the pile retaining wall deformation, basically the lateral deflection. As the red line shows the first excavation stage, there were 3 excavation stages for this, and hence you can see how they followed each other and how they incrementally, either the ground settlement increased or and as well, and also the lateral deformation. So basically there is a definition that soil loss volume can be calculated as the area of the ground settlement between the ground settlement curve and the horizontal axis. And also the volume increase is the area between the lateral pile deformation and the vertical axis. So in this case, they did a calculation of did the volume really increase, or was there soil volume loss, and they found that the ratios were slightly beyond 1, suggesting more volume loss rather than volume increase, soil volume increase, and this was attributable to some consolidation, self-consolidation of the ground. So on the two walls of retaining pile walls, you can see the kind of lateral deformation that was seen. And essentially, there are two modes that came out, two lateral deformation modes. One side is the cantilever mode on the right side. So left side is cantilever mode, and then the right side is the prop mode. So the right side is the side that is next to the tunnels. And on the left side, there is no tunnel. And what does that, the conclusion from that is then that the presence of a tunnel will actually affect the mode of deformation, of lateral deformation of your excavation. So the questions you guys were asking when we were talking about Abraham's paper and whether there is an effect of having, a tunnel nearby. So the tunnel also does affect how the mode of deformation you are going to see, lateral deformation you are going to see on your excavation. So as you can see, again, we are back to that plane strain ratio phenomenon, which basically, as Professor explained, is that whenever you are near a corner, there will be a corner effect on the lateral deformation or displacement. But if your excavation is long, so long that you are very far from the corner, especially in this particular excavation, consider it this way. This is a very long, deep excavation. So I would say somewhere here in the middle is very far from corner effect. I mean, it's also in literature, it's been defined like if a point is about 30 meters away from a corner, then already the corner effects will be diminishing. So here we have a situation where, of course, this was a 132-meter long excavation. So there's a good chunk of this excavation that it should be free of corner effects, and therefore the deformation in this area should be 2D. Rather, it should be, plane strain ratio kind of analysis should suffice, and that is what was. So there was a revisiting of the plane strain ratio calculations for this excavation, and the range was found to be between 0.69 to 1.0. So at 1.0 it means that in that section, there is no deformation lengthwise. The only deformation that this cross-section will be experiencing will be XY, but in the Z, which is Z, if you consider Z, no, Z will be not depth. Okay, maybe in the Y direction or X direction, this direction of the tunnel, call that X direction. So there will be only two axial deformations rather than in the direction of the tunnel, longitudinal direction. And the ratios, when the PSR is near 0 or towards 0, then it means there is 3 XYZ deformation strains are happening in that section. So we found that, of course, this is the value of ground of strain strain ratio that were calculated in this study. However, using other earlier formulae, they were getting higher values of plane strain ratio. But then it was noted that the ground characteristics of the other, upon which the other calculations were based, were not the same. So ground stiffness does affect plane strain ratio. And this is something maybe you can take into our future practice, that whenever you have a differing plane strain ratio, different from what is maybe found in another piece of literature, then consider ground stiffness as one of the effects that can affect your value. So we needed to do then to now explore the effects of the tunnel of the excavation on the tunnel or the deformation on the tunnel. Then we needed to do a numerical analysis, which was done. Here was done a numerical analysis in Praxis. And first, to start off, is basically a sort of form of calibration, which is you run the Praxis and then you compare with field readings, site, in situ readings of your instruments. And that was done. And it was found, there was a good fit between what Plaxis gave as a lateral deformation and what was read off the field instrumentation. And that means our numerical model was fit for purpose to be used now to do the rest of, the machinations, the rest of to try and find out the rest of the interactions. So in this part, what is to be noted is that they were using hardening small constitutive model as well as HSS. HS, hardening soil model, and hardening soil small models were used in this. And the other, one of the key things that came out was in ground responses is that the lateral displacement of the wall, of the retaining pile walls, between when there is a tunnel beside it and when there is no tunnel beside it, came out with the conclusion that the presence of a tunnel does not largely affect the lateral wall deformation. Remember, keep in mind that we said it affects the mode of deformation, where we talked about cantilever mode and probe mode. That was noted, but in terms of the magnitude of deformation, there was not much influence. So then that means now let's go back to the other side. What was the impact on the tunnel by the excavation? And as you can see from this figure, you can see what was previously a circular tunnel starting to become egg-like. So that means the excavation was actually affecting. You remember the instrumentation we had put on the tunnel? The prism marks, they were now giving us these results. And the strain gauges, etc. So you can see that the shape of the tunnel is changing into egg shape, even though, of course, this is a magnified result, but in reality, the displacement or the changes were about 5 millimeter, but now this is a magnified result, and you can see some sort of rotation so it means the axis, the tunnel will be, if you excavate near a tunnel, there will be some rotation of the tunnel, as well as the shape, the cross-sectional shape of the tunnel will actually change. So that's something to bear in mind if in future you are going to be in charge of an excavation near an existing tunnel. Another aspect that was explored was really longitudinal strains, whether there was, and okay, of course, also one thing you need to check is here, besides the changing shape of the cross-section of the tunnel, you can also note that it is actually moving. There's some settlement, sometimes some uplift, also some settlement of the tunnel. So it's like changing it from its initial position. And these are crucial points to take note of. If maybe the tolerance of your tunnel is such that it's not allowed to settle much, then be careful about an excavation near your tunnel. Then, of course, then now I'm talking about longitudinally. What was noted, the vertical and horizontal tunnel displacements on the right right side of the tunnel, you can see were documented as follows. And therefore, also, we were able, based on the strains that were read off the strain gauges, the vibrating wire strain gauges that were put on the tunnel reading segments, you can see you were able to calculate the tunnel shear force on the segments. Key to note from that calculations was that, the presence of bolts that are connecting the segments, which are able to take more tensile stress than the concrete itself, were a damping factor, of course, on the shear forces and bending moments and all this. So conclusions, the PSR was determined from as ranging from 0.69 to 1.0. They did note that some readings that were made of the lateral deformation may not be really accurate due to position of installation of the inclinometer. Perhaps it would have been installed deeper. The issue of stress relief of the ground caused by nearby excavation would significantly increase lateral displacement, but an existing tunnel has limited influence on the lateral displacement. This ideally comes from, let me take you back to the beginning. What they noted is that the excavation for the station, in this area, there was more lateral displacement than the tunnel. And you can know, I mean, the station is definitely deeper and bigger, so there's a lot more stress relief than the tunnel. So that is the basis for that conclusion. And then the prop mode and cantilever mode show that distance from the excavation site could affect lateral displacement, because we are talking about the two sides of our deep excavation. So the side which is next to an excavation or either for the station or the tunnel, you can see was affected and it had a different mode of deformation. Nearby tunnel underwent deformation, which I've shown above. There was some cross-sectional changing. There was some rotational clockwise rotation under the asymmetrical stress relief that was caused by our deep excavation. Then maximum tunnel deformation and distribution of circumferential bending moments of rings closely related to bolt positions. I've already said that. And also maximum longitudinal strains, lining strains occurred around excavation center. This is the place where we had plane strain ratio of 1. And just like the tunnel maximum displacement, with inflection point of 0 corresponding to a point of maximum shear. Thank you very much for indulging me.
Okay, thank you. I think, Maria said, I think this paper exactly cover what Abraham and Desmond Chill present before, right? Because we all talk about the excavation of how excavation affect the nearby existing underground station and subway. But for Abraham's case, it's in the two sides, but actually we are in the same side. And also mention about PSR. But again, I want to address one thing about the reliability of the monitoring system, just like you mentioned in your conclusion. The toy of the incrementers very likely may, because it's too shallow, so may underestimate the lateral displacement which we have. And and I think this paper talking about two ways. One is about the existing subway tunnel and the station's impact on the excavation itself, and the other is talking about the ongoing excavation, how it affects the tunnel and yeah. Okay, so just one question for you. I mean, why it affects the tunnels? Seems it affects tunnel more rather than the station. Any idea? Why the excavation affect the tunnels more rather than?
I think I would put it this way, that the stress relief that is occasioned by the excavation
no, I think
is a lot more on the tunnel than on the to cause an impact on the tunnel, because the area of interaction between these two facilities. The deep excavation is the station is very big,
Yeah,
is
of course, if you're talking about the stress relief caused by tunnel itself and the excavation, of
Mhm.
course, it's caused by the tunnel is much less. Oh,
Yes.
but that's an impact on the ongoing one. But what I'm talking about is ongoing excavation, why it affects the tunnel more rather than the station.
Oh, okay.
Why?
The tunnel more. I
Okay, I think the you think about the overall structure of a tunnel and the excavations.
yeah.
Which one is more rigid? The station is more
The
rigid,
station is more rigid.
so that's the reason why. I mean, it affects tunnels more.
Oh,
So
yes,
that's the
yes.
reason why. That's the reason why they're talking about. Do you remember in the paper they're talking about the movement of the boat,
The
even
bolts, yes.
the boat, and then and the significant effect the water bending moment and actual force on the tunnel segment. But we don't talk about anything about the station,
Yeah, yeah,
right?
true. Yeah.
Because the reason is the station structure itself is much more rigid rather than the tunnel.
Thank you, Prof.
Yeah,
Yes.
I think that's a very, very important issues which we
Point.
and of course stress relief stress relief issues. The other PhD student in Indonesia, which I also assist, right? He's working on that. He's working on that, because in Jakarta MRT, we also have a similar situations. I mean, so perhaps Abraham, your paper you can upload into the link later on. Coco is going to to open the link to let you upload the files. So I will quite. I'm quite happy to see you upload both the paper and the PPT because like
Okay.
the paper you mentioned, I mean we are really we got somebody who really working on these stress relief issues,
Okay.
and and I think can be a and also Moriarty also mentioned about the ground stiffness.
The ghost
So
thing.
because as you can see, we do have a distance
Mm.
from the station to the
Yeah.
existing station to the excavation, even though that's not far away, but I think our ground is much stiffer. So that's the reason why, I mean, not affect that much. So, I mean, but I think the stress relief issues indeed is there, and we will have to explore more. And even how you're going to consider the stability of the excavation under that because for the excavation stabilities, what we always need to get is kind of a stability safety factors, right? For under that kind of a case, how are we going to get a so-called safety factor? That's also the other issues which we may have to talk about. I mean, discuss more later on. Yeah. So really, I mean, your presentation today, I think is quite useful, really. Yeah. And yeah, Moraji, thank you very much. Yeah, because we have to move on now. It's already 10:30. Yeah. Okay. So next will be
Sorry, Benson.
yeah.
Benson, I may ask that me or Jerry or Benson Jr. can presentation first because we have final exam at afternoon and we should
Okay, sure.
print
Yeah.
the sheet, that
Okay,
sheet first.
okay.
But Professor, we have a problem. We are going to pray after
Yeah,
this
they
because we are too
also
late.
Oh,
they I mean let's say hey how much time you need the print the exam sheet.
It is already Professor 10:28.
I know, but I think Mickey they how you if we let's say we finished at the 12, can it be possible?
I don't know what if the 那个
Yeah,
学
because
校
we
的影音室有没有开，我不知道他中午
你
有没有
们要去
休息。
你们
对，要
要去
去
是
对戏班那边，对，
要去，他中午可以啦，他们中午有
他中午可以。
人在啊。对啊，对啊，对啊，哎呀，他即便你们是1点半开始考嘛，对不对？
我们1点考。
哦，1点开始考。
Yes.
应该12点进去，他应该还可以印啊。对，因为他们是11点半要去那个清真寺啊。对，对啊。
Okay.
OK， 好。Yeah, I mean, so we try to be quick 啦。Okay, otherwise
Okay.
you guys may be late for I mean to go to the mosaic. Okay, yeah. So we still, so Majid, please, yeah. Hello, Majid. Yeah.
Yeah, Professor.
Yep.
Can you see me now?
Yeah, it is appear. Yeah, it is clear.
Okay. Good morning, everyone. Today I want to present to you the finite element analysis of a deep excavation. It is a case study from the Bangkok MRT. Actually, I want to here discuss only one station, that is the Blue Line, Sukhumviti station. Not working. It's slide button. Yeah. Now we can see introduction background. Bangkok is located on a thick river soft clay deposit, making geotechnical design difficult. Soft soils are sensitive to deform excavation, can cause excessive settlement and damage of adjacent structures. Predictive movement use finite elements method (FEM) is complex due to factors like mesh generation, ground conditions, and constitutive soil models. The main objective of this study is to perform a 2D FEM study of a deep excavation to evaluate the performance of 4 different constitutive soil models against field monitoring data. This is the station. You can clearly see this one station, which in this paper have been discussed about this station. Case study of condition. Project overview is a part of Bangkok MRT Blue Line, which is actually 22 meter long and have 18 stations. The station which we discussed here is Sukhumviti station. The width of the station is 23 meter and length is 200 meter and the depth is 211 meter. Construction method is top down technique using the diaphragm wall. The thickness of this D wall is 1 meter and 27.9 meter deep. Excavation depth is maximum depth of 21 meter at stage 4. Monitoring. Monitoring is the instrumental which are used to monitor the, in this instrument is inclometer, surface settlement arrays, and building settlement points. Case study generally focus on the inclometer 4 because due to minimal corner effect. The soil condition here is geological condition. It is deep soft clay deposit. You can clearly see there are some mere clay, Bangkok soft clay, and different types of soils here, different type of layers of soil here. Bangkok soil profile, it is 0 to 1 meter. From 0 to 1 meter, it is a made ground, and from 1 to 14 meters, it is soft to medium stiff clay, and from 14 to 26, it is stiff to very stiff clay. From 26 to 37 meter, first and sand. Groundwater found at 1.5 meter depth, but deep aquifers have substantial piezometer drawdown due to years of deep well pumping. The software which are used here is Plex 2D version 9. Geometry, only half of the station was modeled due to symmetry, because only he can discuss about the one half of the station because it is symmetrical. They can only discuss about the one half. The station dimensions are 23 meter wide, 200 meter, which we already discussed in the previous slide, 23 meter wide, 200 meter long, and 21 meter deep. Here also you can see the 1 meter diaphragm wall has been used for the support, and which is up to 27.9 meter. Average element size is 2.53. 649 elements has been taken here. A fine mesh of 2054 elements showed. This shows the fine mesh elements and the coarse mesh elements. They show the same result, so that they decide to take the coarse mesh elements 649 as compared to the finer mesh 2054 elements, so that the coarse mesh was used for efficiency. They can get result fast as soon. Pore water pressure, a critical finding. The study compared the hydrostatic versus drawdown pore water profile. You can clearly see in this figure. This is the wall movement and depth and the distance from wall to the surface settlement. Hydrostatic. This is the you can see the dotted one. This is the ground result, and this one the black line. It is a drawdown, and this one is hydrostatic. The hydrostatic shows overpredicted wall movement by 200% and suggested instability. The drawdown necessary for reliable analysis in Bangkok matches field data much better as compared to the hydrostatic. The study compared the following models. In the study, they compared 4 constitutive soil models. First one is Mohr column model, MCM. It is simple, elastic, perfectly plastic, uses untrained shear strength and elastic models. You can clearly see here also. This is the ground data. Here the dotted one and the black one. This is in the MCM data. You can clearly see the ground data is more as compared to the Mohr column model shows here. The second one is hardening soil model, which is stress dependent stiffness, different stiffness for load versus unload reloading. This one also shows much better result as compared to the Mohr column model. You can clearly see the ground data and the data we chose from HSM, and also from hardening soil model with the small strain stiffening HSS modifiers of HSM. It is a modification of HSM. HSS is the modification of HSM, accounting for high stiffness at very small strain levels using parameter Gmax. This one is the only one. It shows the better result as compared to the other three. This one, you can clearly see the wall movement and the depth and distance from wall and the surface settlement. This one covers all the data which are available in ground data, and this data is looks like the same. And a soft soil model SSM based on critical state soil mechanisms. It is good for compression of soft soils. Now it is the comparison of all the HSS, SSM, MCM, all these here and SSM. You can clearly see here. It is the dotted one is the ground data, and this thin line it is the MCM, and the black one it is HSS2, and the dotted one it is SSM, and this one is the HSM. The HSS shows clearly which is a near to the data which are it matches the ground data as so that HSS and the ground data can be looks like it can match each other. Now the lateral wall movement results. Corn effect, which already Moriarty and some previous presenters discussed about the corn effect. Inclumeter data showed corn effect were significant on short sides but small on longer sides. L by B is equal to 8.7, justifying 2D analysis. MCM slightly under-predicted movement, approximately 15% lower than measured. SSM and HSM provided reasonable good prediction for the top part of the wall, but slightly overpredicted deeper over movements. HSS yielded the best prediction for maximum wall movement at the final excavation stage. MCM, the ground surface settlements here, results of the ground surface settlements. MCM failure produced a shallow and wide settlement profile. Predicted maximum settlement was less than half to the actual field measurement. SSM is better than MCM, but still showed a similar wide trend. HSM predicted better settlement envelopes, spandrel concave shapes closer to reality, but the HSM shows nearly identical profile to HSM, agreed well with the field data. The challenges of small strand parameters. HSS requires the threshold near strand parameters gamma 0.7. Soft clay empirical method worked well for Bangkok soft clay. Scientifically empirical method failed under predictor movement significantly. Solution is a base calculated gamma 0.7 or 0.002% was required for clay to match field data. This is now we can see the conclusion here. Drawdown is essential. Realistic drawdown pore water pressure must be used for Bangkok excavation. Hydrostatic assumptions led to errors. Model hierarchy. Accuracy, we already discussed here in previous slides that HSS shows the more accuracy as compared to the HSM, SSM and MCM. MCM limitation is simple. MCM analysis is reasonable for wall movement but poor for predicting ground settlement. Parameter selection. Accurate prediction depends heavily on selecting relevant parameters, especially small strand stiffness for stiff clay. Thank you so much.
Okay, thank you. I think we try to catch time. Two key issues here is, okay, for excavation, because the retained site and the excavated site, the water ground level definitely different, right? So in
Yes.
general, it does have a C page, but we didn't, when we do the, when we have a class, we didn't mention that much. But as you can see from Majid's, presentation, it does cause a kind of a difference there. And second thing I want to mention here is talking about a constituted model, because the constituted model is kind of say a model which you have to choose in order to properly simulate the soil behaviors. But I'm going to give a course talking about the constituted models next semester, but it will be in Chinese. So I would not recommend you to take it. So just let you know, say constituted model is a model which you should choose in order to properly to simulate the soil behaviors. Okay. So these are two key issues there. Okay. Thank you. So we should go next will be Mio. Hello, Mio, are you ready?
Yes, I'm ready.
Okay, please. Yeah.
What the this? Okay. Can you see my presentation?
Yes. Yep.
Yes.
Okay, so good morning. I'll be presenting a paper titled Influence of Deep Foundation Pit Excavation on the Stability of Adjacent Ancient Buildings. So it's a paper from Journal Buildings, and it was published in 2023. So about the background, we know due to the rapid urbanization, there's been a lot of modern construction, and some of the times this construction is near to the historical sites, and such as ancient buildings, and these buildings are often constructed with brick or wood, and they are highly susceptible to disturbances. So the deep foundation pit excavation, there's a possibility of slope instability, and this possesses risks to these ancient buildings. So the case study which we are going to see is a case study in mainland China. It's in Xi'an, and it's basically a regular foundation pit of about 60, 20, and 15-meter deep. And the adjacent ancient building was a Wan Yuan Pavilion, which is located just located at a distance of about 6 meters. And this building is a 2-story brick, and it's a wooden structure. And the challenge here is that we have to ensure the stability during a multi-stage excavation process using MSJ piles. Here you can see this is the building, and these are some of the instruments like A1, A2, A3, and A4 on this building, and some instruments to measure the deformation at B1 and B2 near the pit foundation. And here this excavation was carried out in few stages. So the methodology for this project was they did first on-site monitoring to measure the deformation, and then later on they carry out the numerical simulation using the finite element analysis. And finally, they simulated the staged excavation in 4 vertical layers, as in the what they are going to do in the on the site. So for the numerical simulation, they used the Midas software and they carry out the 3D finite element analysis. The model size was 150, 110, and 45 meters, so that they can avoid the boundary effects. In order to simulate the soil, they use the solid elements. For the walls and the beams, for the walls and the pit floor, they use plate, or you can say shell elements, and for the piles, they use the beam elements. So for the soil model, they use the Mohs column model to simulate the soil, and for boundary conditions, the top face was free and all other sides were fully fixed. So here here are the model parameters. You can see the thickness, cohesion, friction, and unit weight. And this is the comparison between the measured values and the values from the numerical model. So overall, the numerical model validated the observations from the site, the observations from the points as I earlier mentioned, A2, A4, and here the B1, different stages. And here you can see the comparison between the models with and without the piles. Here you can see if we don't use the piles, there is a lot of settlement, which you can clearly see with the in the first figure. And if we use the MSJ piles, the settlement is quite low. So without MSJ piles, the settlement goes up to 45 millimeters, and with MSJ piles, it's reduced to only 15 millimeters. And here you can see the edges, the building wall, like without the MSJ piles, there is a lot of damage, particularly accumulated on the first floor, and with the MSJ piles, there is a much less damage. So overall, from this study, they concluded that with MSJ piles, it can reduce the settlement up to 66%, and that will keep it in the safe limits. So the discussion here, the mechanism of action. So MSJ piles, they act as a stiff barrier. They improve the soil modulus, and they effectively blocking the transmission of ground movement from the pit to the building foundation. And the numerical simulation results shows it was validated, and with the field data, and the use of Morse column model for the complex excavation analysis. For the practical implications for engineering practice, prioritizing reinforcement and building corners and opening is crucial. And MHA piles should be designed to match the pit depth for the cost-effective safety. And for the conclusion, the primary cause, the differential settlement is the main driver of the shear strain in adjacent ancient buildings, leading to a potential structural inclination. And for the effectiveness, MSJ piles are highly effective. They can reduce the shear strain by about 66%, which can prevent or minimize, prevent the structural damage. And for the design rule, in order to ensure safety, MSJ pile depth should be at least equal to the excavation depth, and monitoring should focus on the corners as well as the windows. Thank you so much.
Okay, thank you. I think the two key issues which I want to mention here is, I think this paper talking about how protection measures effective, to reduce the impact from the excavation to an ancient building, right? That's a issue
Yes.
one. Yeah, and issue two is, I think in their models they try to build the above structures in the model, right?
Yes, yes.
Yeah, that's something which I always have some doubts. Because I mean, geotechnical software has its own limitation, so which I think is good for the underground, but for the things above ground, I'm not sure how good it is. So that's I think the doubts which I always have, in case you have to put any above ground structures in the model. Yeah.
Mhm.
So maybe that's something which has to be discussed later. Okay. Yeah. Thank
Okay.
you. So
Thank you.
for next, Risky. Please. You can start it if you. Hey, Risky, can I hear you?
We don't hear.
Yeah. Hey.
Hello?
Yeah,
Can you hear
yeah.
me?
Okay, yeah.
Okay. Okay, I would like to present today. It's about the large deformation problem arising from the excavation in silt strata. So
Wait
I
a second.
will.
We cannot see your PPT.
Oh, second. Okay.
Yep.
Okay. So I get this paper from Journal of Rock Mechanics and Geotechnical Engineering. The author is Sui Feng O, Wei Liao, Xiang Shou Cheng, Ko Fu Yang, Ashraf S. Osman. So this project is about the Cat and Cove metro station with the excavation depth. It is 2. For the cross section, it's about the on the silt soil is about the 16.68, and for the transverse section is 23.8 meter. And also this excavation will divide it by 2 sections. Is section 1 and section 2. Section 1, the length of 237.1 meter, and the section 2 is 235. 0.9 meter. And for the soil characteristic, the silt layer thickness is 46% of excavation depth. For the key property of the silt, so the water content it's about 70%, and also the friction angle is about 2.7 degree, and the cohesion is really low. It's about 10 kPa. For the pipe monitoring result, there is two things that we can see. That for the figure, this figure it's giving us information about the displacement of the maximum horizontal displacement is 137.46 millimeter. It's 3.3 times above the standard. The standard about the 40 millimeter. And also for the ground settlement, the picture is illustrates the diagram wall deflection and ground settlement at C4. It's evident that the wall deflection exhibit a distinctive bulging pattern. So, however, what the wall deflection and the ground settlement values are all above the specific control value. For exceeding the control value of 0.0025 HA, the maximum wall deflection was observed as a depth of 2.32 meter below the excavation bottom. So the measure maximum ground settlement about the 153.91 millimeter. This is significantly exceeded the control ground, the settlement value. And also for the file monitoring result, there also have 4 factors that we think it's show correlation between the measure maximum wall deflection and the excavation depth. The value at the transport section were found to be in close agreement with a finding. The value in section were considerably larger than those previously reported. An excavation depth of 16.65 meter in section A, and the maximum wall deflection reached is like I said before, it's 137.46 meter. So for the mechanism and numerical analysis, they have 4 factor. The factor is about the retaining structure stiffness, the strutting system stiffness, length of the diagram, and also the soil strength. The relationship between normalized wall deformation and the factor discussed above are plotted at different silt layer thickness. This figure 15 demonstrates that the influence at the various factor on the wall deflection varies. The degree of change at the normalized maximum wall deflection by the retaining structure stiffness, routing system thickness, length of diagram wall, and the soil stirred. Within the normalized value is about the for the retaining structure stiffness is 0.18 or 80%. For the routing system stiffness is the deformation it's about the 3%. For the length of the diagram wall is about 0.3%, and the soil strength is about 27%. It will give us the information that the main effect of this problem is about the soil strength. So depend beside of our program by the soil strength. So the author or the researcher have two treatment. This is silt transformer. We use jet growthing, and also the increase the diagram wall of the thickness. When we see after we give treatment for 2 cases about the wall displacement and the ground settlement. So from the ground settlement, if you see at the previous that our ground settlement is about 150. Right now after the treatment, it's become the 40 millimeter, and also for the deformation of wall, as we see at the previous before the treatment, the value is about 137 point something millimeter. I'm sorry, I forget about the value. And right now after the treatment, they increase about this 40 millimeter. So the conclusion from this paper, we can see the significant deformation in the expressed street strata is mainly caused by soil creep, so that deformation continues to develop even after the base slab is constructed. So even after the base slab we constructed, the deformation still continues. So the dominant factor that I say before is about the soil strength when we compare with the wall stiffness, root system, and wall length. And the most effective component of this combination of structural reinforcement and diagram will increase, not just structural reinforcement alone. So the proposed handling method has proven to be effective with a reduction in wall deflection and ground settlement around 70 until 80%. So that is my presentation. Thank you very much.
Okay, thank you. I think again, two things which I may want to remind here is in this paper it does talk about several factors how they affect the deformations which we have from the from the excavation, right? Yeah, but the other thing is very important is okay. Actually, if you look at the observation value, the deformation comparatively large, reach 150 millimeter something, right?
Yeah.
Because originally in our paper we're talking about 0.5% to 0.2%, but they reach 0.6%. But in fact, the excavation is still there. So really, sometimes when you want to talk about say, oh, what is the so-called alert level, you still need to see whether or not okay. I mean, one thing is about say whether or not this deformation is going to affect the stability of excavation. The second is whether or not this is going to affect the structures nearby. If there's nothing nearby, even having a little bit larger displacement is still acceptable. Because in Taiwan normally say, oh, we no matter what case it is, they always want to control the displacement, say less than 30 millimeter, which is like 3 centimeters. But sometimes I would say maybe not necessary. Okay. So that's you can see from this case. Even the displacement is comparatively large, but the stability of the excavation which is still there. So that's no problem at all. Okay. Yeah. Okay. Thank you. So next will be who? Nareen. Risky next one will be Nareen, and then Rosie, and then Tofik, and then I try to let you all finish before 11:30, and then you can leave first, and then 3 Taiwanese students. And Lily, you don't have to go anywhere, so Lily can be the last one. Okay. Yeah.
Okay, Professor.
Yeah. So, Noreen, are you ready?
Okay.
Yeah, yeah.
Before that, I asked Rosie to help me to do the share screen because my laptop has a bad connection. So I will do the presentation with my phone.
Yeah, you can go. I mean, even your phone, it's okay. Yeah.
So good morning, everyone. Today I will present a journal about influence of the excavation-induced ground movement on adjacent piles. Okay, next. The background and the problem of this study is deep excavation causes ground movement, which can affect nearby pile foundations. Therefore, it's important to predict pile deformation and bending moment induced by excavation. Next. The main aim of the study is first to investigate the pile behavior due to lateral ground deformations caused by nearby excavations, and the second one is to develop some design charts to predict pile behavior. Next. The next is model validation. Before conducting the parametric study, the numeric model is validated using centrifuge test data from previous research. The comparison shows good agreement in pile deformation and bending moment, which confirm the reliability of the model. As we can see, the picture, the A is pile lateral deformation and B is bending moment along pile shaft at the end of the excavation. Okay, next. And the parametric study is conducted using a three-dimensional finite element model and the cross-section of the three-dimensional problem analyzed is shown in the picture below. The soil is assumed to be clay, and the material properties used for the clay soil are shown in the table 1. And the table 2 is about material and geometric properties used for the parametric study. Okay, next. The analysis of results. A is effect of excavation depth. As the excavation depth increase, pile lateral deformation increase approximately linearly. The maximum pile deformation is about 1% of the excavation depth. Similarly, the pile bending moment also increases with excavation depth, with the maximum bending moment occurring near the depth of maximum pile curvature. We can see the picture, the lateral deformation and the bending moment. Okay, next. And the next is effect of pile location. When the pile is close to the excavation, deformation and bending moment are large. As the pile moves farther away, both deformation and bending moment decrease quickly. Far from the excavation, the pile mainly moves without much bending. And the picture is about effect of pile location. The top one is pile lateral deformation and the below one is the bending moment. Okay, next. And the third one is effect of wall support system. Increasing the spacing between struts leads to larger pile deformation and bending moment due to increased wall and ground movement. Similarly, increasing the stiffness of the struts significantly reduces pile response, although beyond a certain stiffness level, the effect becomes less significant. Overall, the wall support system plays a critical role in controlling excavation-induced pile behavior. We can see the picture below. The first one is effect of vertical spacing of support system. And the right one, effect of spring stiffness. Okay, next. Next. D is effect of soil and pile properties. The picture shows the effect of soil and pile properties. Higher over-consolidation ratio means stiffer soil and smaller pile deformation. Pile head condition has strong effect on bending moment. A fixed pile head produces a large bending moment near the pile top. Okay, next. And this is the design chart. The design charts are used to estimate pile lateral deformation and bending moment caused by nearby deep excavations. They are developed based on the result of the parametric study and expressed using influence factors. The pictures below shows that the influence factor increases pile deformation but reduces bending moment, and the unsupported depth becomes larger. Okay, the picture is influence factor for unsupported depth of excavation corresponding. A is deflection and the B is bending moment. Okay, next. The conclusion of this study is, first, deep excavation induces ground movement that significantly affect nearby piles. Among all factors, the unsupported excavation depth has the strongest influence on pile response. And the proposed design charts provide a practical tool for preliminary design. Okay, next. Okay, thank you.
Okay, thank you. I think again, because we from this paper, because for the previous paper we're talking about the impact from excavation on tunnel, on excavation, but not on piles. So your paper, cover something which we missed before. And one thing which I probably want to add comments is, okay, even though, okay, if you want to reduce the influence for the excavation on the piles, even pile itself, you can try to aid the pile head. Because the pile, if you can have a fully fixed pile head, looks like you can reduce the displacement and the bending moment a lot, right? Yeah. So that's something which I want to address. Say, even though you have the pile you design is very slender, not very tight, not very large, but and can be easily affected by the excavation. But if you change something in the pile head, looks like you can reduce the impact. Okay. So thank you very much. Yeah, because I need to finish before 11. You got 2 more to finish before 11:30. So next will be Rosie.
Okay, Prof. Wait a minute.
Yeah.
Is it clear?
Yep.
Okay. Good morning, everyone. Good morning, Prof. Today I will present a comprehensive study about this paper, journal paper by Wang, Su, and Wang in 2010, which, wait. Yeah. Wall and ground movement due to deep excavation in Shanghai soft soils. The paper was published in Shanghai. The paper was published in the Journal of Geotechnical and Geoenvironmental Engineering as ASCE. This research is particularly important because it provides critical empirical data, field measurement data from actual construction sites that directly impacts how we design and construct the deep excavation in soft soils conditions. All right. The research background and motivation. Shanghai has experienced rapid economic growth, which has driven numerous deep excavation projects for high-rise buildings and subway networks. The main engineering challenge here is that excavations are becoming both deeper and larger in scale, which often being constructed in very close proximity to existing buildings and infrastructure. Since 1990s, performance-based design based on acceptable movement limits rather than just strength calculations, has been adopted to protect adjacent properties. Accurately predicting wall deformation and ground movement, how much the retaining wall will bend, how much the ground will settle, remains the most challenging task for engineers working in urban soft soil environment. The objective of the study is to collect and analyze extensive database of wall displacement and ground settlements from Shanghai deep excavation. And second is investigate characteristics of wall deformation and ground movement patterns. And the third is provide practical guidance for predicting movement in soft soil conditions. Okay, database and the methods. The researchers collect and analyze 300 case histories from Shanghai, making this the most comprehensive study in for this region because have a lot of case. There are 32 cases using the top-down method where permanent floor slabs provide support during excavation. There are 200 cases of relative stiff wall, including diagram wall (DW), and contiguous pile walls (CPW), compound deep soil mixing wall (CDSM), all combined with structural elements. All constructed using the bottom-up method where temporary struts provide supports. Additionally, there are seed pile walls (SPW), compound soil nail walls (CSN), and deep soil mixing wall (DSM). Okay, the maximum lateral wall displacement results. Figure 3, as you can see in here, present the relationship between maximum lateral wall displacement, how far the wall moves horizontally, and its maximum points, and excavation depth, h, how deep we dig. The results show several clear trends. First, the top-down construction method produced the smallest displacements, ranging from 0.1% h to 0.55% of its h, with an average of 0.27% of h. This means for a 10-meter deep excavation, the wall would typically move only 27 millimeters. And second, bottom up. Construction with stiff wall DW, CPW, and CDSM solve maximum displacement of ranging from 0.1% of its height to 1% of its height, with an average of 0.4% of its height, meaning 40 millimeters for a 10-meter excavations. And the third is SPW, seed pile walls. It's much larger displacement, up to 3.2% of its height, with an average of 1.5% h, or 150 millimeters for 10-meter excavations. And then there is a compound soil nail walls (CSN) for the average of 0.55% of its height, while deep soil mixing wall (DSM) average is 0.91%. And is this for the maximum lateral wall displacement results? The figure 4 reveals where along the wall the maximum displacement occurs. Generally, the maximum lateral wall is observed between 0.5 h and 1.4 h depth below the ground surface. More specifically, 53% of cases saw maximum displacement occurring at 0.5 h to 1 h depth, while 43% saw it at 1 h to 1.4 h. The ground surface settlement characteristic. Now moving to the ground surface behind the wall, figure 9 shows that maximum ground settlement, how much the ground surface sinks at its maximum point, range from 0.1% of its height to 0.8% of its h, with an average value of 0.42% of its h. This means For a 10-meter deep excavation, the ground will typically settle about 42 millimeters. The settlement magnitude increased proportionally with excavation depth h, meaning that deeper excavation caused more settlement. Figure 10 illustrated that the settlement distribution pattern across distance from the excavation. The settlement influence zone, the area affected by ground settlement extended from 1.5 h to 3.5 h distance deep from the excavation edge. Maximum settlements typically occurs within 1 h distance from the wall. The relationship between maximum wall movement and ground settlement. The figures 12 demonstrates a clear correlation or relationship between wall displacement and ground settlement. The ratio between delta VM or delta HM maximum ground settlement divided by maximum wall displacement range from 0.4 to 2.4 with an average ratio of 0.9 or approximately 0.69. These findings means that the ground settlement magnitude is approximately equal to wall displacement magnitude in Shanghai subsoils. This finding is consistent with previous research by Goldberg et al. In 1976 and Moorman in 2004, who found ratios of 0.5 to 2.0. So the implication of this design is now the engineer know that the slight trend for decreasing displacement is increasing, and systematic decrease in deflection with increasing thickness from 600 millimeter to 1000 millimeters. Factor of safety tendency for decreased displacement with increasing VOS against basal heave, independent of displacement for stiff walls once it's guaranteed. So, engineering implications for design practice. For practical design, this research finding provide 4 keys insight. First, the top-down construction method minimized wall displacements to only 0.27% H compared to 0.% H for the bottom-up method. This makes the top-down approach preferable when strict movement control is required in sensitive urban area. And then second, increasing wall penetration depth beyond what is required for stability does not significantly reduce displacements. This allows for more economical design because engineers do not need to specify excessively deep wall just to control movement, as long as basic factor of safety FOS requirements are satisfied. And the third, the settlement influence zone extending from 1.5 h to 3.5 h distance from the excavation must be carefully considered when assessing protection requirements for the adjacent structures. And the fourth, this performance-based design PBD approach, which focuses on controlling movement rather than just ensuring strength, has been validated by this comprehensive database of 300 real cases. The conclusion of and research contribution to conclude this study makes several significant contribution to the geotechnical engineering practice. First, it provides the most comprehensive database for Shanghai deep excavation with 300 case histories. The second is quantify clear displacement patterns with the specific numbers that engineers can use. Wall displacement range from 0.27% of its H for top-down construction, which is the best performing methods. And then the recommendation is top-down method prepared for the minimizing movement in urban areas. System stiffness and VOS have measurable but moderate influence on performance. Proposed upper bond settlement provide applicable for Shanghai soft coil conditions. Result provide useful guidance for prediction movement in similar soft soil environment. Okay. Thank you very much. This is my presentation.
Thank you. I think, I think one thing, you will have to think about that. Very interesting, because for this paper it uses 300 sets of the data, right? And both wall deformation and ground settlement. And but that's a paper in 2010. So most of the work they did is by visual checking and the hand calculation, right? But now we do have a tool called AI.
Oh yeah.
So yeah, if we use okay, let's say 15 years ago, they use a visual checking and the hand calculation, got the results like what you have now. But now, if we use partial AI, partial visual inspection, what the result will be. And then if we do that fully in AI, whether or not we will have the same conclusion. And of course, AI, we will have a different algorithm, which one, different one may give you different results. So I think that's something which we will have to think about very, think about later is because many works before they, for example, like this paper, they do the feature checking, but right now actually you can put it into the AI and that AI to run directly, but whether or not we will have the same conclusion.
Oh, okay.
Right, 300 set I think is enough for us to do the AI analysis, is it?
Mhm.
Yeah. Oh, so that's something which we can think about later on. Okay. Oh.
Okay.
Yeah. Okay. Topic, you are the last one before 11:30.
Wait a minute.
Yeah.
Topik use my laptop because his laptop can speak.
Okay. You are everyone's operator.
Wait. Yeah, this one.
Okay.
It's good. Okay, bro.
Yeah.
Okay.
Topic, you are ready. You can start it. Yeah.
Okay, thank you very much for opportunity. Now I want to explain or discuss about this topic. This topic, the name is evaluation of the wall deflection of a deep excavation in Central Jakarta using 3D modeling. This project, from I think this is the Prof Benson project. The 2018 years later ago. Years later. So for the interaction, Jakarta is the capital of larger city of in the Republic of Indonesia with a population of 20 million and limited urban public transport survives. So the concept of this project is a PSR or Plan Start Ratio proposed by Outlet 2006 is used to accurately quantify 3D excavation induced behavior from the output of two-dimension FE analysis. The PSR is the ratio of the maximum wall deformation of a section of a wall at the distance from the corner to the maximum wall deformation of the section under plane strain condition. So 3D FA analysis was the conduit to model the selected deep excavation in Central Jakarta and to verify the applicability of 3D FA model in predicting 3D excavation wall replacement. And so the construction was performed using top-down method with 5 excavation stage supported by 4-level reinforced concrete slab with a variation thickness. So this paper present a case study and numerical simulation regarding a large-scale deep excavation in Central Jakarta, Indonesia, at its 3-dimension 3D effect on wall deformation. So this is the cross-section and soil profile of the excavation, top-down construction method, and 1430 meter excavation length, 22 until 30 meter excavation width, and 18.9 meter excavation deep, then retaining wall, diaphragm wall, and support slab. And you can see this the picture, two pictures about the construction. The first picture is about overview, and the second picture is plus view. For the first pitch, we can see the excavation area and slab opening for TBM and section D to D. And this is the construction space and section of the excavation. The prep wall installation until 101 elapsed day, and for the first excavation to the deep to 1.5 meter, 18 days, and for the second excavation to the deep minus 5.8 meter, 30 day, third excavation to the deep 11.18 meter, 22 days, and fourth excavation to the deep to 17.53 meter, 28 days, and the last excavation to the deep to 18.93 meter. And this is the plan view of the excavation with the inclumeter section and location instrumentation. We can see the part of inclumeter, observation wheel, borehole, and the last pressure meter, and what downhole seismic. We can see this picture about this for park. Okay, next. This is about profile of subsurface soil information. The part A, water content, plastic limit and liquid limit. The part B, sand content, C, fineness content, and the D part is void ratio. And the second page, profile of in situ information. The part A, SPT, and the part B, CPT, connect resistance, and the part C, CPT, friction resistance, and the part D, Serwolf velocity. And this is the second table, input soil parameter in AS model. You can see this part. And the next, this is the 3D FA analysis, also called BIGMAR analysis, was conducted to examine the performance of the excavation in this study. This is the 3D fine element model of BIGMAR analysis. And this is the comparison of result from 2-dimension plan state model and 3-dimension unit lake model. The part 1 wall deformation, then the part B wall bending moment. And the second pitch is PSR curve for Jakarta clay and comparison with observed PSR. So the conclusion, this paper presents a case study and numerical simulation for the 3D effect of large scale deep excavation on wall deformation in central Jakarta, Indonesia. We can see this is the 4 pitch about variation of PSR width at various BBL. The part A 0.5, the part B 1.0, the part C 2.0, and the part D 3.0. And the last conclusion, the study conclude that 3D effects should be considered in the excavation design, especially near corners. The basic car profit particle to convert 2-dimension analysis result into realistic 3-dimension. Additionally, soil stiffness plays a crucial role in both PSR and wall deflection behavior. Okay, so this is my presentation, and I say thank you.
Okay, thank you. I have to say, when we work for this paper, we really look into every detail of this paper,
Yes.
the case history and write this paper, and even up to now, 2025, when I met the PT MRT Jakarta people, what they told me say, for the excavation in Jakarta, this is still only one journal paper which they can refer for the excavation in Jakarta, and it's written by Taiwanese.
Yes.
That's what they told me. So I do think later on in Indonesia, no matter where it is, I mean, especially in the major cities, you do need to have a more researches about the deep excavation because I know many deep excavation projects are ongoing in the major cities there. Okay, so for those people who need to go to Mosaic, you can leave now, and I will say happy winter break to you. And I think the first week of January, I starting from first week of January, I will still go to the university. I mean, say from time to time. Okay. Oh, so is that okay?
Thank you,
Because I
Prof.
think,
Thank
yeah,
you very
most of the,
much.
yeah, thank you very much. Oh, so now will be the Taiwanese student team, right? The
Okay,
turns,
Prof.
right? Thank you.
Enjoy,
Okay.
enjoy
Thank
your
you.
holiday,
Bye. Bye.
everyone.
Happy
Take care.
holiday.
Bye-bye.
Bye.
谢谢 Professor。
Bye. Yeah.
Bye bye.
Okay.
Prof,
Bye. Okay.
Prof, can I leave too?
Yeah, sure. You want to leave? Okay. You are not Muslim, right?
Yeah.
I mean, okay. Yeah. If you want to leave first, no, you can leave it too. Okay. Yeah. Okay.
Okay.
Oh,
Okay.
yeah.
Thank you.
Okay.
Professor, you said before the link will be sent, right, for me to send the article plus the PPT, right?
Yeah.
Okay.
Coco will do that. Okay.
Okay.
Hey.
Okay.
Okay. So who will go first? Benson Junior, I saw you on the screen. So what you do? You still feel sleepy?
No. Okay.
Okay. Yeah.
I
Okay. I think it should be enough for you three to finish before 12.
okay.
Yeah. So okay, yeah.
有
Yeah, we Didi and Moriyasu became only two, right? Hey. So Risky, you don't go Mosaic today.
No, I go. I just
You
wear
go,
my
okay.
shoes.
Oh, okay, yeah. Because I mean I say, hey, how come you still there? Yeah.
So
Okay.
do I have to cover it in English?
Of course.
In
Oh,
English.
Of course.
okay.
Any course.
I fully recall. I fully recall today's presentation. Okay. Yeah.
Okay, wait a minute.
Yeah.
Okay, I'm going to talk about basically about something deep excavation and buttress wall. This is the title of the paper, and it's mainly written by these four people, mainly Oh Yuzhang, this person, and some and other people. Oh, Oh
Yeah,
Oh,
and the first one is 谢百沟，那谢行风，谢百沟。Originally, he was teaching in 华夏。
谢百沟，我不知道怎么翻译成这个。Okay. And this is my flow chart here, and we're going to things we're going to talk about. Okay, let's first check on the site, and the excavation site is located at Taipei. For a reminder that Taipei is basically soft clay because of the basin, and the scales there is basically 7 basement and 38-story building. And the excavation depth is 26 meters. It's quite deep basically because Taipei we're facing soft clay. So it seems that 26 is not that deep, but it's kind of hard to excavate. The method here is top-down method. So when during the excavation, the slab is also will be finished during the excavation. And the challenge here is that the D walls because of the the place there, and a lot of neighborhood house, a lot of house nearby. So there are some challenge. The strict there are strict displacement limits. I think is the deformation of the wall or displacement or the settlement. There are some limits in that case. So with the D-walls during the construction, D-wall must have some. There should be some additional reinforcement. So basically, it's just the buttress wall we're going to talk about. In Chinese, 就是扶壁。跳不了。Okay. And second, we're going to see about the geotechnical condition. Geotechnical condition, basically, you can see the soil layer on the left-hand side. Basically, basically soft clay to silty clay, and then about 40 meters deep, there is a gravel layer. So the wall is the D wall is going to go so deep, about 40 meters or 43 meters deep, to touch the gravel layer. Okay, and the sequence of this excavation is going to there are 8 stages in this excavation. So like a picture on the right, the picture right hand side here. Okay, and then the things we're going to talk about here is in this paper they use 3D analysis, 3D numerical analysis, and in the right hand side picture you can see that basically finite element analysis. Why they really want to use 3D because it's the L over B, B over L. B over L is approximately 2.5, and you can see the picture here. So the PSR ratio is considered because the corner effect there. So the 3D spatial effect is significant. Okay. Then we're going to talk about how it chooses it's how the soil model is, and then the 3D numerical analysis. So basically, the soil model they use is hardening soil model, and like it just mentioned in previous previous report there. So I just briefly introduce. So if the hardening soil model, basically the Young's modulus, the modules will change with the stress difference, and also during the unloading reloading there will be a different Young's modulus. So basically the concept here is the Young's modulus is not constant. This is different from our well-known Mohr-Coulomb model. Yeah. So the table down here is their parameters, the number they key in. Okay. And then they use Plexus 3D with the finite element method to mesh. And then we calculate the deflection of the D wall. And you can see that the prediction here, they use Plexus 3D to make the prediction, and this SI 2, 3, 4, 5, 6, 7 is basically the different location, and then we will see the the site, the position later. And you can see that the initial prediction of the SI5 here is the largest deflection is 80 millimeters. It's kind of large because the regular limit is 50 millimeters. So you can see that here is quite large. So the prediction here after the analysis that something must to be some support needed is needed. Yeah, is required. Okay, so they came out to mind is but buttress wall, which is 伏壁 in Zhongwen in Chinese. This is basically what buttress is usually it provides some effect like a T-beam, so it help to side the literal soil pressure to add more resistance for during by friction, I think. So the design of the buttress wall, you can see that here. This is yeah, you can see that a different location, which is SI 6 1 2 3 4 5 6 7, and then this something stick out here is just buttress wall, and the type ABC. There are just some different design. Like you can see that the type C is a little bit longer. The AB type is 5 meter long, and C is 7 meter long, and the thickness is varied from 0.6 meters to 0.8 meters. And you can see the design here, the different different angles.
Different cross section.
Cross section.
Different,
yeah,
different cross section. Okay. Yeah.
Okay. Quickly on the first prediction we talked about here, I just mentioned is the prediction here is yellow line, blue line here, and then during the construction, during the excavation, there are monitoring data over here, which is a black line, and you can see that the black line and the prediction is kind of far away, although the prediction is larger, but in this case, the prediction and observation can they be the same result because of the only one site. So that means their prediction the prediction needs to be fixed. Yeah, because it's too large. The prediction is considered too conservative. So usually they think, oh, that's okay because prediction is larger, observation is smaller. You think that maybe it's okay, but for the engineer, the not accurate is also means risks. So basically the first model there is not representative. It's not representative enough. So the model must to be correct, and then so they do the back analysis. That is after the excavation is begun. So the left hand side figure shows the corrective prediction. Basically, they correct the Young's modulus they use, and then the interface reduction factor. Let me introduce these factors briefly. It's basically kind of like a friction. They fix this friction and the Young's modulus, so the model is more accurate. And then you can see that the red line is the corrective prediction. It's more close to the observation, and then the observation and the corrective prediction, the largest deflection is about 30 millimeters. Okay, so let me make a conclusion there. The first one is the observation is about and prediction match because they fixed the model. It's about 30 meter, and the efficient of buttress wall, you can see that we okay. You can see that the buttress wall, if there are buttress wall, so they can here like this picture. RDD means without minus with buttress wall and divided by without buttress wall deflection. So you can see that the buttress wall is reduce the about 15 to 27% deflection. Yeah, during the top-down excavation. And then the key point is the back analysis here. In practice, there are some model. When we first build the model, and then we found that the model is not correct enough, so we have to check again the parameters there, so that the monitoring system can ensure the stability and safety, and then the model is more valuable. So that means lower risk. Okay. Okay, thank you.
Okay, thank you. I think several things which I want to say here is okay. Benson Junior, do you want to go back to your last slide?
Okay.
The final one. Yeah, you have a comparison there, right? So in fact, I think the prediction, the reduction ratios from the prediction is still less than what the reality is, right? And I believe the main reason is, I mean, because the buttress wall actually it had two different functions, you know, in for the excavation. One, especially in clay, is to increase the wall stiffness. I mean, think about it, because the wall original is, let's say, 1 meter, 1.2 meters, but if you add additional buttress behind, the wall stiffness, overall wall stiffness became larger, so supposedly can reduce the displacement. And the second thing is, if you have a wall, I mean excavation, especially in sand, the buttress and the soil, it has a friction force, right? It has a friction force. So that's a but right now in the models which you use, I believe you use plate element to simulate the buttress, right?
Plate. Okay.
Yeah, plate element. So that's the reason you only have a one parameter called the R ratio, the R inter. But in fact, if you want to present the friction force, supposedly you should be able to add the parameters to show how the friction force is. But this part is ignored in your model. So that's the reason why I think you predict, right? You know, because reduce factor, reduce ratios in the prediction, even you do the correction, is only like a 17 to 20. I think in your last page, 17 to 20%. But in fact, the reality is 19 to 30 something.
19 to 30.
Oh. Yeah, 19 to 30. It means in reality it can reduce more, but in the numerical simulation, you reduce less. And I believe that basically is the friction force between the wall and the buttress wall and the soil are ignored. So that's a reason why. Yeah, that's a reason why. I mean, you have a less, the predictions rather than the realities. Oh, okay.
Okay.
Oh, yeah, good. Yeah, hey, let us talk about this a bit in Chinese. 你们3个要去戏班子，要去印东西。
我们等一下要去，对，去戏馆的2楼吧，还是？
去2楼，对不对？啊，2楼那个随时都可以印，不是吗？
我们没有印过，我们之前都是用自己，我们之前都是自己的印表机
2楼的他只要有密码都在外面啊。因为这样就没有12点钟的限制啊。因为我以为说是你们要跑到西半就可能会有12点。那2楼它不是机器行在外面。
对。
对啊，那只要有机器密码，那就没有12点的限制了。
好。
对啊，因为我就担心说你会不会，那如果这样的话，你们就可以结束再去印这样就好了。
可以啊。
OK， 好，嘿 ，OK，yeah. So who will do, Jerry or Miggy? Want to do next?
我先好了。
Engage, please.
OK. Okay. And good afternoon, Professor and everyone. I'm Jerry. Today I will be presenting on the performance of excavations with COSWORTH. This presentation is based on a study by Professor O and his team, published in ASCE, which analyzes a real-world case study of the UPIB building in the Xinyi district of Taipei, UPIB building. And at first, this is my outline. First, I will explain why we need the COSWORTH method. Then I will introduce the background of the UPIB building case history. Next, I will explain the mechanism of COSWORTH and the critical aspects of their construction. Finally, I will discuss the effectiveness and conclusions by comparing field monitoring data with numerical analysis results. And let's start with the background. The biggest challenge for deep excavations in urban areas, especially in soft clay, and is excessive ground movement, which often damage adjacent buildings. Traditional solutions like underpinning are too costly, and conventional struts are usually passive, installed only after excavation has begun. Therefore, we introduce COSWORTH. These are underground walls constructed perpendicular to the diaphragm wall before excavation starts. The goal is clear: to provide strong lateral support in advance, thereby minimizing deformation right from the start. And in this case, we use this COSWORTH in this figure. And the case study for this research is the UPIB building in Taipei. The geological conditions here are very severe, with a thick layer of soft clay reaching 51 meters here, along with the high groundwater level. This project involves a very deep excavation of 32.5 meters, and here, with diaphragm was reaching 57.5 meters. To control deformation, the engineering team installed 3 COSWORTHs, each 1 meter thick and 45 meters deep, effectively partitioning the long sides into smaller compartments. And mechanism of crossworks. So there are two main mechanisms. First is the corner effect. The connection between the crossword and the diaphragm wall creates an artificial corner, just like leaks, and providing high stiffness. And second is partitioning. It divides the large excavation into small zones with better aspect ratios. However, success depends entirely on joint quality and joint. The sling between the diaphragm wall and the crosswall must be thoroughly removed. In this case, high pressure water jets on steel brushes were used to clean the joint, ensuring the concrete bonds tightly for effective load transfer. And next part is here. To validate the effectiveness, this study used two-way validation approach. First is field monitoring using inclinometers to measure wall deflection and settlement points for ground settlement. Second, numerical analysis using a finite element model that considers small strength soil behavior. Our logic for comparison is simple. We compare the measure data with crosswords against a simulation without crosswords to quantify the specific contribution of the crosswords. And the figure is the comparison. Look at the data compared to the simulation without crosswords and the locations where crosswords were installed. This line is the analysis result, and other lines are measurement. We can see wall deflation was reduced by approximately 75%. Ground settlement was reduced by approximately 82%. Furthermore, observations shows that movements near crosswords were minimal, behaving very similarly to the stable corner of a diaphragm wall. And conclusions. Here are the three main conclusions of this study. First, effectiveness. Crosswords significantly reduce deformation and settlement in deep soft clay. Second, mechanism. They function similarly to the corner effect, providing stiff lateral constraints. Third, construction. Success relies on joint quality. Sling must be completely removed for the crosswords to function as intended. And thank you for your attention.
Thank you. I want to address two things here. Okay. First of all, about the mechanism. I would say the crossword mostly just like one additional strut in the ground, right? Because you connect the two sides, so just like a strut. Okay, so it does have a function of the strut, but just below the excavation level instead of the above, right? And if you compare your result with what Benson Jr.'s papers, you can reduce up to 75% or even 80%, right?
Yeah.
Yeah, but for Benson Jr.'s paper, buttress were only, what's the maximum value? 30 30%. So which one is better?
This one is better. Crosswalk.
This one is better, right? Yeah. But why people still prefer to use a battery sword sometimes instead of a crosswalk?
Maybe，我可以讲一点中文吗？有的我不太会回答。
Yes, yeah, you can.
我觉得是体积的原因吧。battery sword 就是一部分而已 ，crosswalk 这样吗？
Okay. I want to put in two aspects. One is whether or not you have the certain condition to do the crosswalk.
Yes.
For example, if your excavation, your width of the excavation is very wide.
Yes.
Or there's non-rectangular one. Can you make a wall between two sides? Right, that's one thing. Two, do you think which one is more expensive?
Crosswalks.
Yeah.
就跟这张图一样嘛，太宽就没办法用。
Yeah. That's the reason why I say, two issues. One is whether or not you have that condition. 你有没有那个机会 Do you have that chance to build the crosswalk? 因为如果你今天很宽 the excavation is really wide. 那你这样子一做，你可能很难做，或者是经济性不好，对，然后再来你的价钱可能也比较高。So I think there are two main reasons why. I mean, sometimes we still need to consider battery sword instead of crosswalk. Okay. Yeah. Okay. Thank you. 你们其他课还有用英文做 present 吗？
没有，这是我第一次用英文报告，所以我
第一次用英文报告。
对。
Okay. Yeah. 没关系，但是我觉得总是要有第一次啊。
谢谢熊老师给我这个机会啊！
没有啦，而且我觉得，那我们等一下你们还有时间吗？因为好像你们东西印好了，是不是？
目前的问题是蔡老师忘记密码，所以我们印不出来。
阿北，
那
就不是那就不是我的问题。
对吧？
没事，他想起来了，他有跟我说。
所以嘉轩等下可以去处理，对。所以我们不用赶12点了哈。对。
Yes.
Okay. Yeah. So next, Mickey, please. Yeah.
Okay.
Yeah.
Thank you, Professor.
You're welcome. Yeah.
Hold on. Okay. Can you see my PowerPoint?
Yes.
Okay. And today I'm talking about the system stiffness and wall displacement of a deep excavation strengthened with cross walls again in soft clay. Yes. And this paper is done by Dr. Xie's team, and it's published by the Journal of Geoengineering in 2019. And here's all my content. First, I will introduce about the cross wall, introduce about the background of the site, and then I will introduce about the cloud scheme. And next, I will talk about the analysis of the case and the revision of the parameters. And finally, is the conclusions. Okay. And first, in practice, accurate assessment of the wall displacement has important on the overall success of the excavation project. And we can use simple empirical equations or numerical models like Placis or Torsa to perform the estimation based on the budget or the complexity of the excavation project. And nowadays, the crosswalls are extensively used in excavation projects. It is obviously that the overall stiffness of retaining system is dramatically increased with the presence of the crosswalls, and which also makes it more complicated to estimate the wall displacement. And this paper devises a systematic approach to estimate the strengthening effect of cross walls on both system stiffness and the factor of safety against basal heave.
Then in practice, the design engineers prefer a simple and fast approach to estimate the possible wall displacement. And to fulfill this purpose, in 1989, Clough developed a scheme based on the concept of system stiffness and the factor of safety against the basal heave. And just like this chart shows, and the x-axis is the system stiffness, and the y-axis is about the wall displacement, and the number on the curve is the factor of safety against basal heave. And they do some tests on this case. This case is located at Shilin district of Taipei City, and which is an area notorious for its thick soft clay and high groundwater table. And to strengthen the retaining system, here are 4 cross walls were constructed. And to measure the wall displacement, here are 6 inclinometer casings were installed in the diaphragm wall. And it's obviously to see that the Clough scheme overestimate the wall's displacement without considering about the effect of cross wall. You can see the red here. Yes. And the corner effect is enhanced because of the cross wall. As a result, they use PSR to consider the contribution of the cross wall. And PSR is just like we just talked about that. It means the plane strain ratio, which is 3D divided by 2D. 2D means plane strain, yes. And because of the cross wall provides the additional lateral resistance to the retaining system, so the factor of basal heaves should revision. And also, cross walls can provide additional side friction against the soft clay. And they assume that the friction is related to the adhesion between the wall and the clay. And for simplicity, assume that the adhesion is the same as the shear strength of clay. So the shear strength should be revised. Yeah. And the adjust of FB. FB is the factor of safety against the basal heave, and you can use these two formulas to count. But this SUB should change like this. It's the average of the original and the revised. Yes. And in the original design curve, it has some limitation, like the system stiffness should be less than 3,000, and the factor of safety should be less than 3. And this curve may not enough to use the sides with cross wall. So they use a simple curve fitting technique to extend the curve into low displacement area. So you can see the right hand side of this chart. The stiffness can larger than 3,000, and the FB should be can be larger than 3. And it's obviously to see that the revised predict wall displacement is not that overestimate the real measured displacement. Okay. And at the last, they also use Plexis for predicting the wall displacement. And this table are the parameters they use in the Plexis. And the comparison of predicted wall displacement and field measurement shows that, and the delta Clough is about 84 times magnitude of the delta field, and the delta revised is about 14 times the magnitude of delta field, and delta 3D is in Plexis is about 4 times the magnitude of the delta field. And the results means that the revised scheme is much improved than the original scheme. But still deviate from the 3D and the field results. And I can make some conclusions. First is the field measure of wall displacement strengthened by the cross wall is too small to use the Clough scheme. So we should revising the system stiffness and the factor of safety against basal heave. And next is using the extrapolation technique can extend the curve. Okay, and the predict wall displacement using adjust parameters are much better than the original Clough's prediction. And finally, is the revised scheme and the extended design curves have the potential to serve as a reliable tool in estimating the wall displacement for excavation with cross walls in soft clay. Okay, here's my presentation. Thanks a lot.
Okay, thank you, Mickey. I think this paper mainly talking about, say, they want to use a kind of equivalent unjoined shear strength and still use Clough's Clough's chart to interpret the displacement. But in fact, I think still what they predict still more than the reality, right? I think. Yeah.
Yes.
Okay. But I think because I don't know whether or not this is a paper written by Dr. Ari and Professor O. Because if you go back to the figure talking about the safety factor, the Terzaghi, you have one figure show the Terzaghi safety. Yeah, this one. Yeah. Do you think they should add something there to consider their safety factor? Because yeah, I think one factor very important, but they totally ignore.
One factor.
Yeah, one factor. We say that's very important when we calculate the safety factor against, for the excavation, but not be counted in this equation.
Not counted.
Not counted. I think that is quite important factor, but not counted here. Anyone had any idea? Not counted here.
厚度吗？那个什么东西？
厚度是一件事。Wall thickness is one thing, and how about the other? The other even more important, I think. Of course, wall thickness. But what the papers which Moriarty, present. Of course, wall thickness is one thing, but the other things even more important. Especially because for wall thickness, when we calculate a safety factor, it is not available, right? Yeah, wall thickness is there because when we talk about I, the system stiffness, the system you have the moment of inertia, wall thickness you calculate that, but there's one more thing, we don't count it. Anyone realize that? Okay, maybe I can give you an answer. The embedded depths of the wall.
Oh.
Right? Because they don't talk about. You think about if you have a longer wall or shorter wall, whether or not this is going to affect your safety factor. Yeah, but they don't count it. So I think that's one thing which, in case now later on you want to work on the soft clay, to define the safety factor with no matter cost wall, buttress wall case, that's something which they may have to consider because I personally think, especially for the excavation in soft clay, this is a quite important factors. But they don't count it in Terzaghi's equation. So that's the reason why they got much bigger. They predict much larger displacement rather than the reality. Yeah. Okay. I think that's something quite really important. Yeah. Yeah. Okay. Thank you, Mickey. So we come to the last one, Lily.
Yes, Professor.
Yep. Yeah. Your turn. Yeah.
Professor, can you see my screen?
Yes. Yes. Yes.
Okay.
Yeah.
So my paper is analysis of world and ground movement due to deep excavation in soft soil based on a new worldwide database. It is mainly written by Christian Moorman, and it is published in Soil and Foundation in the year 2004. It's mainly gonna based on it's mainly gonna focus on the database of 530 current international cases, which are taken from like 1980 to 2001. Which is gonna which is gonna provide us the data of the world and the ground movement due to excavation, and then the groundwater condition and other geometrical boundary condition were also considered in these cases. Mm, uh, the results of the previous empirical uh, data were also considered in this case. So we're gonna go to the second slide. The background and motivation. The background and motivation behind this study was in the urban areas there are often deformation and ground settlement which affect the structure, and then the performance of the structure depend on the soil condition, excavation depth, and support system, wall stiffness, and the construction method. So in this paper, some cases like Park, Cuff, and Oroki's cases were considered, and then data were taken from those cases, and new data were produced comparing all those data. The study complete about 530 international case histories about the deformation of the soil. So here is the database overview. 536 worldwide cases histories were taken mostly from 980 to 2001. The excavation covers soft clay for which the CU is less than 75 kilonewton per meter square, and then stiff clay, non-cohesive soil, layer soil, and rocks. Detailed documentation like soil and groundwater condition were considered, excavation geometry, and the wall type, what type of wall were used, sheet pile, diaphragm, shoulder pile, and second pile, etc. Support system like the brace and it was top down. As we can see, the zone 1 sand and the soft of sand and soft to hard clay, average workmanship, and very soft to hard clay. They were divided into zone 1, 2, and 3 in this paper according to their type. The key parameters considered in this paper were excavation depth, the depth of the excavation, age as shown in the picture, the maximum depth of the excavation, and then the maximum horizontal wall displacement, UH max, as it can be seen in the paper here. I mean the diagram, UH max here in front of the pile, and then the maximum ground settlement UV max here, the settlement of the ground, and then the support spacing and embankment depth, the system stiffness, and then the factor of safety against basal heave. So the horizontal movement the main finding in this were that according to this empirical study, that the soft clay shows the largest displacement and scattered typical ranges from the soft clay, like the UH max as shown in the here, the UH max, the maximum horizontal displacement, It ranges from 0.5 to 1%, which is average of 0.87% in stiff clay and sand, and UH maximum, which is greater than 0.25, the height of the excavation, and then the maximum wall displacement typically occurs at from 0.5 to 1 below the ground surface level, and we can see some of the data comparison for the maximum vertical settlement behind a retaining wall with maximum horizontal displacement on the wall. That one is diagram 1, and then diagram B, standard and settlement profile depending on the type of the, it is taken from Goldberg et al. Paper 1976. This empirical data. Then the ground settlement main findings. The main findings of the ground settlement were the settlement are significantly larger in the soft clay, as mentioned before, and then the average normalized settlement in the soft clay is like 1.1% the height of the excavation, and stiff clay is 0.18% the height of the excavation, sand 0.33% the height of the excavation. Maximum settlement generally occurs within 0.5% with X less than 0.5% behind the wall. In soft clay, settlement influence many extend to X approximately equal to 2H, posing risk to nearby structure. The risk is higher in the soft clay. The risk of settlement is higher in the soft clay. And then the relationship between the wall movement and settlement, as we can see, the ratio vertical settlement versus horizontal settlement is commonly from 0.5 to 1. Occasionally it goes up to 2, as shows in the picture. Occasionally we can see that the horizontal went to 2, but in most of the cases it's like 0.5 to 1. Constant volume assumption in Park in 1969, not supposed to be enlarged database. Settlement mechanism include wall deformation, groundwater drawdown, and stress relief due to excavation. The system stiffness, a critical insight. Contrary to common design assumption, increasing wall or support stiffness does not proportionally reduce the movements. Wall displacement show that we got no correlation with support spacing or embedment depth. Overall system stiffness, once a maximum adequate stiffness is achieved, other factors dominate behavior. As you can see in the diagram, the soft soil horizontal wall displacement versus stiffness defined by Cuff et al. 1989 figure. And then dominant controlling factor is the basal heave safety factor. In soft clay, factor of safety against basal heave is the most influenced parameter. When the basal heave safety factor is less than 1.5, rapid increase in the wall movement was noticed, and empirical limits proportional by are largely confirmed. Empirical limits proposed by Mana and Kulf in 1989 are largely confirmed, as we can see in the diagram that when the basal heave movement was less than 1.5, the wall movements were rapid. And then the practical implication, over stiffness retaining system is not an efficient displacement control strategy. Greater attention should be given to basal stability. We should give attention to the basal stability, excavation sequence and workmanship, groundwater control, and time-dependent effects in cohesive soil to prevent the deformation, to reduce the deformation in the soil, rather suggesting potential for more economical excavation design, rational optimization rather than conservative stiffness acceleration. The conclusion for this is, the main takeaway is the soil condition and the excavation depth dominate excavation performance. Soft soil soft clay excavation required basis stability control rather than excessive stiffness. Wall and ground movements are empirically predictable within board ranges, not exact values. Large database provide more reliable design guidance than isolated case history. We can see the deep excavation in soft clay depending on the safety factor against the basal heave. Compaction of the approach by Manas and Kauf in 1981 with the result of new database. We can see the Manas and Manas and Kauf 1981 database, and then we can see the new excavation line, new database against that. That's my presentation. Thank you.
Okay, thank you. Lily, are you all right? I mean, looks
Yes,
like
Professor.
yeah, because why I heard it seems you have a runny nose or
Oh yeah, Professor, is because of the, I think, sudden cold in here, so that's why.
oh, so that's all right. Okay. Anyway, just a quick question. I mean, in fact, your paper, the moment one. Okay, you also heard the presentations.
Yeah.
I mean, talking about the 300 cases from Shanghai. So, in your view, what's the main differences between the paper's moment right and the one from talking about 300 cases in Shanghai? What are the main differences?
Professor, I think the main differences is the number of the data collected, because in these cases, like around 536 data were collected, but in that case, like only 300 data were collected. So, because there are more data, so it is possible to have more accurate result. It is possible.
Okay, I think of course the number of the cases is one issue, but I actually have the other view of that is for the previous one, they only talk about the excavation in Shanghai, so for the ground condition is more consistent with rather than what you have, right? Because you have the case in sand, you have the case in stiff clay, in soft clay, but what they have, they fix one factor. I think that's something which you may also need to use or learn, for your later research, because you cannot change the factors all the time. So for the case, which they have in Shanghai, they fix. I mean, one terms is the ground in Shanghai. So very likely you can control a certain variance. Oh, that's one thing. How the ground in Shanghai. Okay, and the other things is you probably can think about, say, okay, I cannot remember who did the presentation, also talking about the curve oral chart, but I think it's either Ricky. I think it's risky. I think risky, or yeah, I think risky, right? Most of the case which they have are within the range of Clover and Orok. But yours, you remember yours, it seems that some of them are out of the range, right?
Yes.
And do you have any idea why?
I do. I think, Professor, is because of the type of the soil. Because
I think maybe that's one of the reasons. You can double check, because supposedly the Clover and Orok chart is only applicable for clay. So, but you do have some cases from sand. So likely that they may be the reason, say, you have something out of the range.
Yes.
So that's what I what I want to comment, in the presentation which you have. Yeah. Okay. Oh. Yeah. Okay. So I think everyone finished the presentation, right? No one. Yeah. Oh. Okay. So okay, if that's the case, maybe we will close the. Mickey, you are still here. I saw you disappear already. Mickey, you are mute. Okay. So is there any other questions? Yes or no?
No, Professor.
No. Yeah. Okay. Yeah. Because yeah.
Happy New Year, Professor.
Happy
in
New Year.
advance.
Happy New Year. Yeah. Happy New Year. Yeah. So I don't know. So Lily, will you join the meeting this afternoon at 2?
Professor, we have presentation from 2
Ah,
to 3 in the
you have a Chinese
class.
class, all right? Yeah, you have a Chinese class. Yes. Okay, so you will not be in the meeting, so, because I want to keep today's meetings shorter, right? So you will be there. Okay, that's fine. Yeah. Okay.
Professor,
Yeah.
if I finish my Chinese class early, I'll try to at least attend the last 30 minutes of the meeting.
I think that's fine because today I think will be quite short, not long one. Even though we may get some new guys attending, but you know everybody is quite busy at the end of term, so looks like the meeting will not be long. So if you can, of course, welcome to join. But if you cannot, then probably I will see you say. I think my next trip to Taichung will be 8th of August. So likely we may have a meeting say in the morning or night or something like that. Okay. Oh.
Okay, Professor.
Okay. Yeah.
I'll
Okay.
try to give you some good like how will I say good presentation about like a review,
and
literature review, and try to learn some software by then. I'll have 2 weeks.
Yeah, and the presentation you met today is using your mobile or user.
Actually, I use the computer from our lab 721.
Okay. Yeah, but how come is the not in a kind of right format? Because if you use a computer, supposedly it should be in the right format, right? But looks like the one you show us. So originally I thought you are using mobile phone.
Yes,
So you-
Professor. I am using mobile phone to give the presentation. Maybe because of that, I think the format got a little bit disturbed because I made the presentation in the computer but presented in the phone. So that
I think next time maybe better because remember like today, both of the Nareen and you know and who else Tawfiq they cannot use a computer to do the presentation, but they pass the file to Rosie to ask him to help. Yeah, so maybe later you in case we next semester we need to do a presentation, so you can do the same. Or anything online if you don't you need to use because I still think use a computer to do a presentation will be better. Yeah. Okay.
maybe I could go to the lab next time and do the presentation.
Okay. Yeah. Okay. So is there any other questions?
No, Professor.
I think maybe Mickey and Jerry not here, right? So yeah. Okay. 你还在啊？
我在。
我在啊。Okay.
我一直都在。
没有，我意思是说 anything else 啊 ？No。
没事。
没事。Okay. Yeah. Okay. So thank you for attending my class today. This semester I will say that. Yeah. Otherwise, you know, the 40. I mean, my class are all foreign students. That's also very strange, right? But at least we finish our task. I mean, in the class all speaking English. Okay. Yeah. Okay. Thank you very much and Happy New Year. Okay.
Thank you very much.
So we are class now. Okay. Yeah. Thank you.
Thank you.
Goodbye.
Thank you. Okay. Bye.
Bye.
Bye. Hey, but how come Irene still online? So strange. Okay. Bye.